All right, the second question on these practice questions that were done in the lab period is Chapter 16, number 4. And they give you a list of species, including HS minus, NO2 minus, HCO3 minus, HBr, OH minus. The order of these might be a little different than what's on your handout, but all the species are here. And then finally water. So they give you all of these species. And just move this over a bit. And you're asked to determine which are amphiproducts, so which can behave as both an acid and a base in water. So the way you answer this is, let's take the first one. Just put it in water, literally, and let's see what happens. Okay, so really there's a question mark here. What happens? Well, it has a proton. It has a hydrogen, and so what if it were to give that up? Then it would become S2 minus, and that proton would then go onto the water, and we would have H3O plus. All right, so that's feasible. Similarly, though, since there is a negative charge here, you might think that it's also a proton acceptor in water. And so if we investigate that possibility, then that would become H2S, and that proton would have come from the water, so in this case water is the acid, and therefore it would leave behind OH minus. All right, so I think, just going to straighten this out, I'm sorry. I think that we would choose HS minus ion as being amphiprotic. So we'll try the same thing with the NO2 minus ion. So NO2 minus, let's put this in water. So it's very much like what we would do in the lab. We'd put it in water and test the pH. Now this does not have a proton on it to give, and so it's not going to behave as an acid, but it looks like it could be a proton acceptor for sure. And it would take that proton from the water, in which case it would become HNO2 and OH minus. Now, since there's no complementary reaction in which this could behave as an acid, then NO2 minus is only behaving as a base in water, and so it cannot be amphiprotic. So we'll go to the next one. HCO3 minus, if I put that in water, it has a proton, which if it came off, that would give me CO3 2 minus, and that proton would be picked up by water. And so it would be behaving as an acid because it's producing acidic conditions here in the product. But because it has this negative sign, it looks like it could also be a proton acceptor, or in other words, a base. And that is true because it would form H2CO3. The proton would have come from water, and then I end up with OH minus. So far, HS minus and HCO3 minus are my two amphiprotic species. HBr, let's just do that one in our heads. HBr is very definitely an acid. Could it be a base? Well, it would become H2Br plus, and that's really unlikely. So let's rule that one out. OH minus, the hydroxide ion. If I put OH minus in water, it's a strong base, so surely that'll turn the solution basic. But can the hydroxide ion also act as an acid? Okay, let's not do that one in our head. Let's actually do that one. Another sheet of paper here. Let's put the OH minus in water. We know that's a strong base, so what might happen here? It would accept a proton and then become, what might it become? H2O plus, what would be left over? OH minus. So it's kind of a equation where we get 1 equals 1 or minus 1 equals minus 1. The question was, could OH minus behave as an acid? Clearly it's a base. Well, if it did, then it would have to give up that and become an O2 minus. And that's just silly. Okay, so OH, the hydroxide ion is not an amphiprotic substance. Let's get that out of the picture. NH4 plus. NH4 plus, put it in water. What can it do? It wants to get rid of that H plus, and so it becomes NH3. That H plus will go onto the water and form H3O plus. Question is then, here we see it acting as an acid. Can it act as a base? Can it accept a proton? It already has a positive charge. That would mean it would be NH5 plus 2, and that's just silly. So the ammonium ion is an acid in water. It's not amphiprotic. And our last one is water. And really what we're writing here is the self-ionization of water. And that, as you know, is governed by Kw. And so one of them is an acid and the other is a base. So if this is an acid, it's giving up a proton, losing an H plus, and becoming OH minus. And the proton that it loses is being picked up by the other water molecule that's behaving as a base. And therefore that becomes H3O plus. So we know that water is an amphiprotic substance. It's the most famous one. But you can basically demonstrate this with one equation. Okay, and let's take this just a step further. We know that Kw, therefore, because if this is liquid and this is liquid and these two are aqueous, Kw is equal to OH minus times H3O plus. But we also know that this is equal to 10 to the minus 14, right? And, sorry, screen was going black. And we know that these are equal to each other, and so this is why this is 10 to the, 10 to the minus 7 molar, and this is 10 to the minus 7 molar, and therefore the pH of pure water is 7, and the pOH of pure water is 7. 7 plus 7 is 14, so it's really like taking the negative log of this whole equation. Okay, that's it for that number 4. We'll move on to the next one.